So the next thing that we need to do is talk about the linear operator. Right? So Laplace transform is a linear operator. So suppose Laplace transform of two functions f1 and f2 exist. Then the Laplace transform of the linear combinations of the two functions is equal to linear combinations of Laplace transforms. That is C1 times Laplace transform of f1t plus C2 times Laplace transform of f2t, where C1 and C2 are constant. So I want to prove this. This is a very quick proof to illustrate this fact that Laplace transform is a linear operator, and we just use definitions of Laplace transform. Very straightforward proof. So if you do Laplace transform of two functions, or linear combinations of two functions, what you can do is you can apply the definitions of Laplace transform. That is the improper integral from 0 to infinity of C1 f1t plus C2 f2t times e to the negative st dt. Right, so e to the negative st is the kernel, is the function specifically for Laplace transform. This is the function that you need to find Laplace transform of. Now, the next step is to distribute e to the negative st into the parentheses. You get the improper integral from 0 to infinity of C1 f1t times e to the negative st plus C2 f2t times e to the negative st dt. Then you separate this improper integral. So integral of a sum is a sum of integral. That is the improper integral from 0 to infinity of C1 times f1t times e to the negative st dt plus the integral from 0 to infinity of C2 f2t times e to the negative st dt. Then remember, C1 and C2 are constant. So when you evaluate the integral, you can pull out the constant. Right? So C1 get pulled out of the integral operation. C2 get pulled out of the integral operations. Then you get C1 times the improper integral from 0 to infinity of f1t e to the negative st plus C2 times the improper integral of f2t times e to the negative st dt. And when you look at this, so there's a dt here as well. So when you look at this integral, you see this is the Laplace transform of f1. This improper integral represents the Laplace transform of f2. Therefore, you have C1 times Laplace transform of f1t plus C2 times Laplace transform of f2t. So we just proved the linearity properties of Laplace transform. So Laplace transform of the linear combinations equal to linear combinations of Laplace transforms. And this is very useful when you find the Laplace transform of the forcing terms, right? The forcing terms can be with multiple terms, can be exponential functions, sine functions, or constant functions get added together, right? For example, in this problem, you have a function can be thought as a forcing term, is the combination of the exponential functions and sine functions. And of course, you don't want to deal with undetermined coefficients or variations of parameters. You can use Laplace transform for this, right? You want to find Laplace transform of this function, that is Laplace transform of f of t, or this is Laplace transform of 5 times e to the negative 2t minus 3 times psi of 4t. And we use the linearity properties of Laplace transform. This gives me 5 times Laplace transform of e to the negative 2t minus 3 times Laplace transform of psi of 4t. And of course, you don't want to find Laplace transform using definitions of Laplace transform. Now we have a tool, which is a table of Laplace transform that you can just utilize. Okay. So let me go back to the Laplace transform table here. So the first Laplace transform is exponential function e to the negative 2t. So you go all the way down here and you look at formula 15. So that is the Laplace transform of exponential functions. Okay. For a in this case is negative 2. So e to the negative 2, Laplace transform of that is 1 over s minus negative 2. So hopefully you follow my analysis there. And the Laplace transform of psi of 4t Right here, you look at number 24. So b in this case is equal to 4. So Laplace transform of psi of 4t is equal to 4 over s squared plus 4 squared. Right, so 2 Laplace transform there. Let me go back to the note. So first, this is 5 times Laplace transform of e to the negative 2t, which is s 1 over s minus negative 2, minus 3 times Laplace transform of psi of 4t, which is 4 over s squared plus 4 squared. So simplify this a little bit. You have 5 over s plus 2 minus 12 over s squared plus 16. Okay, so that's how you perform Laplace transform of some functions added together. So I'm going to move on to doing Laplace transform on some discontinuous functions or piecewise defined functions. The first function I want to introduce to you, and this is a very important function in mathematics and in electrical engineering, because this represents the type of signal that you usually get picked up in electrical engineering. The first function is the unit step function. Step function because you go from here and step it up to another horizontal function. And this is called, another name for that is called the Heaviside function. Heaviside is the English mathematicians who come up with this type of functions. Okay. Again, you're going to encounter a lot of this in mathematics, physics, and especially in engineering. So it's good to know how to perform Laplace transform on this type of function. And this is again called piecewise defined function. So the functions say that when t is less than 0, the function's at 0. You have an open circle here because this is strictly less than 0. And the function is equal to 1 when t is greater than or equal to 0. That's why you have a closed circle here, because it's greater than or equal to 0. So how would you find Laplace transform of this function? You use the definitions of Laplace transform. So Laplace transform of f of t is equal to the improper integral from 0 to in positive infinity of e to the negative st dt, sorry, times f of t dt. So the function is, the Laplace transform is going from 0 to infinity, so the one with t less than 0 is get ignored from this calculation altogether, right? And also at the same time, f of t is equal to 0, so when you put that in the integral, the Laplace transform is 0 anyway. So the focus is only on the Laplace transform from 0 to positive infinity, and therefore f of t is equal to 1. And this is equal to 0 to positive infinity of e to the negative st times 1 dt. And obviously, we have done this already in the first example when you find the Laplace transform of 1. And this is going to give you 1 over s, given that s is greater than 0. So Laplace transform of this unit step function is 1 over s, given that s is a positive number. Now, we're going to move on to another step function. So the step function in this case is the functions from 0 to 3, and f of t equal to 0 when t is between 0 and 3. And the function is equal to 2 when t is greater than or equal to 3. Okay. Because you have t is strictly less than 3 when f of t is equal to 0, I would like to put in an open circle here just to clarify where the discontinuity occurs. Right. So again, we're going to use definitions of Laplace transform to find this Laplace transform of this piecewise defined function. So Laplace transform of f of t is equal to the improper integral from 0 to infinity of e to the negative st times f of t dt. But because you have two different parts to the function, depends on the interval, you break it down into the integral from 0 to 3 of e to the negative st times 0 dt. Because in this interval for t between 0 and 3, the function is equal to 0. And when t is greater than or equal to 3, the function is equal to 2. So 3 to positive infinity of e to the negative st times 2 dt. So it's a little bit different than the last example. So this one is equal to 0 anyway. This, you need to evaluate the improper integral. So we still need to use definitions of Laplace transform at this point. But again, I mentioned before, later on when we get to, so this lecture, let's see, 14, when we get to lecture 16, then we no longer need to apply the definition of Laplace transform for this type of step function. But for now, we still have to go through the calculations. So you turn this improper integral to limit of definite integral. That is limit as n go to infinity of the definite integral from 3 to n of 2 times e to the negative st dt. By the antiderivative of e to the negative st, you have negative 2 over s times e to the negative st, evaluate at 0 and n. Or this is limits as n go to infinity of negative 2 over s times e to the negative sn minus e to the 0. This is from 3 to n. Sorry, 3 to n, and therefore it's not e to the 0 but e to the 3. Then you apply the limit with the assumption is that s is greater than 0, so the limit of this term is going to be equal to 0. And you're left with just negative 2 over s times e to the third power. So negative 3 to the third power. Or you have 2 times e to the third power divided by s, given that s is greater than 0. So that is the Laplace transform of this function. But of course, in practice, you just have the signal. You're not going to see the functions, right? So what you do, you look at the signal. You have to be able to write down the type of function that you are dealing with, or at least the approximations of the functions that you are dealing with. So let's say you have this type of signal, right? And I want to indicate a discontinuity here. So here is 0, open circle. Here's an open circle. Here's an open circle. Okay, let's just leave it like that. Alright, let's write down the piecewise functions that corresponding to the graph that you see here. So there are 3 different pieces that you need to look at. So the functions is going to be equal to positive 2 for the interval between 0 and 4. So this is positive 2 when t is between 0 and 4. And t has to be strictly less than 4 because you have the discontinuity occur there, and the open circle is on the first function. Now for the second function, the function is equal to positive 5 when t is between 4 and 7. Okay, so be careful there. T is greater than or equal to 4, strictly less than 7 because of the closed and open circle. So since the signal stopped at 9, so let's just break it to, so time is between 7 and 9, sorry. Let's say 7 and 9. So t between 7 and 9, and the function is negative 1. So let's not do improper integral here. So still, we're going to use definitions of Laplace transform. Right? So e to the st times f of t for t going from 0 to positive infinity. But you break it down into 3 different integrals here. From 0 to 4 of e to the negative st times 2 dt. Plus the integral from 4 to 7 of e to the negative st times 5 dt, plus the integral from 7 to 9, since that's a lot easier to deal with instead of the improper integral, of e to the negative st times negative 1 dt. So the first integral, you have 2 times 1 over s times e to the negative st, evaluate at 0 and 4. So negative 1 over s is coming from the antiderivative of e to the negative st. Plus 5 times negative 1 over s times e to the negative st, evaluate at 4 and 7. Minus negative 1 over s times e to the negative st, evaluate at 7 and 9. Okay. So you do the evaluations here. You have negative 2 over s times e to the negative 4s minus e to the 0 minus 5 over s times e to the negative 7s minus e to the negative 4s plus 1 over s times e to the negative 9s minus e to the negative 7s. Okay, you can just leave it like this, right? Or you can combine like terms and simplify the problem even further if you want to. So negative 2 over s times e to the negative 4s. So I distribute and then combine like terms. Then plus 2 over s. So negative 2 over s times negative 1 here. That's why I have positive 2 over s. minus 5 over s times e to the negative 7s plus 5 over s times e to the negative 4s plus 1 over s times e to the negative 9s minus 1 over s times e to the negative 7s. Okay. So e to the negative 4s, e to the negative 4s, combine them together, you get 3 over s times e to the negative 4s plus 2 over s, e to the negative 7s, e to the negative 7s. That's give you negative 6 over s times e to the negative 7s plus 1 over s times e to the negative 9s. Alright, so that is the information that you get from this signals that you receive. Let me rewrite this term one more time, the result one more time here. So you have 2 over s plus 3 over s times e to the negative 4s minus 6 over s times e to the negative 7s plus 1 over s times e to the negative 9s. Okay, so what does this even mean? Let's think about this, the result that you just got in terms of a scenario, a real-life scenario. There's two parts to this result for each term in the result. The first one is the fractions. Okay, so you have a bunch of fractions here. I should include the negative as well. Okay, and another part is the exponential functions. So in this case, the exponential function is e to the 0. Right. Now, when you turn on the faucets, there are certain rates on how fast the faucets blow out the water, right? So this is the rate of the faucets, or the rate of the water coming out of the faucet. So this is the rate, this is the rate, this is the rate. Okay. When you originally turn on the faucets, you turn the faucets on at the rate of 2 over s. Right, and I say originally or initially, right, because e to the 0, so time is equal to 0. Right. Now, again, initially, the rate of the faucets is 2 over s. After 4 seconds, or after, let's say, after 4 minutes, you switch the rate to 3 over s. Why after 4 minutes? Because of something called the delay here. So after 4 seconds, you change the rate of the faucet, or the rate of the water coming out of the faucets, to 3 over s. Then at the minute 7, right, what you do is that you get rid of some of the water at the rate of 6 over s. That's why you have negative 6 over s as the rate, and this is the reducing rate. And then at the minute 9, e to the negative 9s, you put in more water, right? So you change the faucets, instead of draining it out, you put more water in the sink at the rate of 1 over s. So this is the type of information that you get when you solve the information when you use Laplace transform to solve the signal that you get. You okay with that? Right, so that is the physical interpretations onto some kind of like real-life example, if you consider it that way. Alright, so that's it for Laplace transform lecture. Now I'm going to move on to the inverse Laplace transform.